If you've ever stumbled into one of those super deep late-night conversations over the mysteries of our universe, you've surely thrown around the terms infinite or observable universe. However, those who are especially curious might raise the question, if the universe really is infinite, how can there be an edge of the observable universe? Well, believe it or not, this confusion actually just stems from a common misunderstanding of the two terms, and hopefully this video can help clear that up. Hi, my name is Oleg, and this is my Astrono-ME Project. As you can tell from the title of this video, I'll be trying to explain the reason for the edge of the observable universe in the simplest way I can while still hitting all the main points. My goal with this video is to make it short, quick, and easy to visualize, and of course to get a good grade in my astronomy course. So let's get into it. First, this video will be split into 3 parts, which will make the topics both easier to explain and to learn. The first section will cover redshift and the Doppler effect. The second section will cover the expansion of the universe, and the final section will combine these concepts to explain the edge of the observable universe. The first concept you need to understand is the redshifting of light. The idea of redshift is very similar to the Doppler effect in sound waves, which is definitely much more intuitive to us. So, I think the best way to explain redshift will be by understanding the Doppler effect and then applying it to light. Let's imagine a scene in which you're standing on the side of the road watching a police car with its siren activated as it speeds past you. From your everyday experience, you probably already know that as the police car passes you, the pitch of its siren is going to change. This is called the Doppler effect. Simply put, when the police car is moving towards you, the sound waves from the siren get scrunched up together, creating a higher pitch. Then when it passes you and starts moving away from you, the sound waves are spread out, creating a lower pitch. We can also use this Doppler shift when we observe light as well. As I'm sure you know, and in case you didn't know, light is made up of waves. Different wavelengths correspond to different colors or groupings of light, for example, infrared light or gamma rays. Because light is made of waves, it too experiences a Doppler effect. When we look at stars, we can take the color of their light and use it to tell us their movement relative to us on Earth. If the star is moving towards Earth, its wavelength will be compressed, which will make the light bluer. However, if it's moving away from us, its wavelength will be stretched, making the light redder, otherwise known as redshift. Astronomers use the Doppler effect on light to help describe the motions of stars and galaxies and understand the universe. What is important to note is that when we observe the very distant stars and galaxies, we find that almost all of them are moving away from us, like you'd see in an explosion. However, unlike an explosion here on Earth, astronomers observe that the most distant stars are traveling away from us the fastest. This will make more sense in the next section when I explain the expansion of the universe and then re-explain redshift. For now, it's just important to understand the concept of redshift. It is a common known fact that we live in an expanding universe. However, there are many misconceptions about the way that it's actually expanding, and it's crucial to properly grasp this concept in order to understand why we live in a limited, observable universe. As I mentioned earlier, all distant stars are collectively moving away from us, and the further they are, the faster they move. So, while our universe kind of looks like an explosion of stars and galaxies through space, a simple explosion wouldn't explain the apparent acceleration of more distant stars. Instead, you should think of the universe's expansion as an explosion of space itself. Rather than all the distant objects moving away from us, it is a space between us and the objects expanding, carrying them away. Here's a great analogy to help visualize this. Take a slightly inflated balloon and a Sharpie and draw dots spread along the balloon's surface. As you inflate the balloon, notice that all the dots spread away from each other, despite the fact that they aren't actually moving across the surface of the balloon at all. The same thing happens in our universe. Stars and galaxies might not actually be moving through space at all, and it is actually the space between them expanding, carrying them away. This model explains much more accurately what we observe in our universe and explains the apparent acceleration of more distant stars and galaxies. The more expanding space there is between two objects, the faster they will appear to move away from each other. You can observe this on the balloon model as well. Now that we understand redshift and the expansion of space, we can start to explain why there is an edge to our observable universe. First and foremost, I need to re-explain redshift with our new understanding of the universe's expansion in mind. While the previous explanation of redshift as a consequence of an object's velocity away from us is a real phenomenon, it is not the main source of redshift in the most distant stars and galaxies. The space between objects is constantly expanding, and a consequence of this is that light waves will slightly get stretched as they travel through it. Think of it as a tiny bit of space being added between this wavelength for each unit of distance the light travels, and as the light travels longer through expanding space, in other words, traveling more units of distance, the wavelength experiences increasing amounts of stretch, which as we know means a greater redshift of the light. As the light continues to travel through more and more expanding space, it will eventually start to approach an infinite stretch to its wavelength. It is important to note that light can never actually reach an infinite wavelength, as that means the light has ceased to exist. However, what an infinite stretch does mean for us is that our current instruments are just not sensitive enough to detect this superstretched light, essentially making it completely invisible to us. So the light is still there, but we don't have the technology to see it. This is exactly what we experience as the edge of our observable universe. The light from stars and galaxies at those distances experience so much stretch that we can no longer detect it. So the universe very well could be infinite, but we just cannot see it because it is too far away and the light emitted from those distances loses too much energy while traveling to us. Hopefully my explanation was clear enough, and thank you for watching.